So we'll start again from here. I had an interesting question during the break about the number of these different kind of stars. It's true that I said nothing about that. And it's quite important to know that in the universe, stars tend to be low mass stars. So most of the stars will be found in this domain here. The more you go toward massive stars, the more rare they will be. So typically in the universe, you will only have a few massive stars for hundreds or thousands of low mass stars. The advantage of massive stars is that they are extremely bright compared to the low mass one, million times brighter of the low mass stars, so they are visible from extremely far away. So we can see them at much bigger distance, so the number we can observe is not extremely small. But still, if you do the number ratio between these two kind of stars, the number will be huge here and very few there. So let's go back to nucleosynthesis and have a look to what happens to the chemical elements inside stars. So after we have determined observationally what is the main sequence, it appeared that this phase during this diagonal in the Hertzsprung-Russell diagram corresponds more or less to the phase where hydrogen is burnt in the core of stars. So the reason is that if you take, for example, in this 15 solar mass stars, the different duration of the different phase of burning, you can see that hydrogen is quite long here, 10 million years. Helium is about 1/10 of the duration of hydrogen, so it is 1 million years. And then from carbon burning up to silicon burning in massive star, it becomes very, very quick. So a few thousand years for carbon burning, few years for neon and oxygen burning, and silicon burning is only a few days. You can see as well that this corresponds to an increasing temperature and increasing density. So hydrogen typically takes place at temperature of a few tenths of million Kelvin at relatively low density. But then when one burning stage is finished, the star contracts, so the density increases and the temperature increases up to it is able to reach conditions where the next burning is possible. So typically for helium, you have to reach a couple of between 100 and 200 million Kelvin. For carbon burning, it's 600 Kelvin roughly, and then for neon, oxygen, and silicon burning, you need to go at above more than 1 billion Kelvin. So roughly 1 billion Kelvin for neon and oxygen burning, and 3 billion Kelvin for silicon burning, with densities that becomes bigger and bigger. So at the end, you have extremely high density near the last burning stages. And again, if you do the same for one solar mass star, obviously you will only be able to go to the helium burning. But again, you can see that the hydrogen burning duration is about 10 gigayears in this case, and helium burning, for example, is only again roughly. Here it's less than 1/10, so it's 100 million years with central temperature that are more or less comparable to here. Low mass stars tend to be a bit denser than higher mass stars, but still the trend of increasing temperature and increasing density remains true here. But the important thing here is that the hydrogen burning time is much longer than all what follows. So statistically, if you observe a star, the biggest probability that you find a star that is burning hydrogen, and very few of them are in the advanced stage. So typically 10% of stars are out of the main sequence, and this is why most of the stars are lying in this diagonal in the Hertzsprung-Russell diagram. Okay. So how do you burn hydrogen inside stars? So you have mostly two channels. The first one is called the PP chains, and basically starts with the protons that are found in the stellar gas. So the steps are the following. You take 2 protons to make some deuterium emitting a positron. With this deuterium, you again aggregate the protons to make helium-3 plus a photon that bring the energy to the star. And then you have different branching of the pp chain. So you have the pp1 cycle, which is basically taking 2 of this helium-3 together, making an atom, a nuclei of helium-4, and releasing 2 protons. That is, so here in the sketch, so you have here the 2 protons that make the deuterium here, deuterium plus protons here that make the helium-3 here. And then you have the different branching. So here it's the pp2 chain that is illustrated. So if you take a helium-3 plus an helium-4 here, you can produce an atoms of beryllium-7 here. And then again 2 branching, beryllium-7 plus an electron that will make a lithium-7, and then lithium-7 plus proton that will make 2 atoms of helium-4. So this is illustrated here, where the lithium-7 here that emits a neutrino and convert one of its protons to neutrons, making lithium-7, and then lithium-7 plus this proton that will merge and release two nuclei of helium-4. The other way is to go through the pp3 chain that takes the beryllium-7 plus 1 protons, making boron-8 that will take a positron and making that will disintegrate, making beryllium, and then the beryllium will disintegrate into helium-4 as well. So these pp chains are dominant up to a stellar mass of about 1.3 solar mass stars, and it is not extremely sensitive to the temperature. So the energy released by this chain is something is proportional to the density and to the temperature at the power of 4. So as density and temperature increases when you go towards the center of your star, obviously it's at the center that you will produce the more energy, and then this energy will be radiated away through the successive layers of the star, reaching the surface at some point. One characteristic of the surface for this kind of low mass stars is that the envelope here in the outer region is convective. It means that radiation is not efficient enough to transport the energy from this region to the surface. This is due to the fact that these stars are quite cool, so the opacity here are quite high. So to transport the energy from here to here, you have to use convection instead of the classical transport by radiation. So it's exactly the same as in pan. When you just boil water, you will have this kind of bubbles developing, transporting the heat from the bottom to the top of your star. This chain produced different kind of energy depending on what branching is taken, but it is about 20-25 MeV per cycle. And this is enough to sustain these stars for quite a long time. When you go to higher temperature, you will be able to activate another kind of burning for converting hydrogen into helium. That is called the CNO cycle. So basically, carbon, nitrogen, and oxygen are used as catalysts in this reaction. And this cycle is dominant at temperature above around 18 million Kelvin. And this one is highly dependent on the temperature. So it's something proportional to the temperature at a power of 17. So it means that your energy production will be extremely peaked at the center of your star, and it is extremely difficult for the star to evacuate this energy. So the only way for these massive stars is to develop a convective core instead of a radiative one, because the energy production is very peaked, and very high. So it's difficult to evacuate this energy. Radiation is not enough, so these stars develop a convective core. And contrarily to the low mass one, as they are hot at the surface, the opacities are low enough to keep the envelope of the star almost fully radiative. So you have the opposite picture compared to low mass stars, where you have radiative core and convective envelope. The massive stars have a convective core and a radiative envelope. Here is the CNO cycle. So you can start almost where you want. Basically, for example, starting here from the carbon 12, you can, by successively aggregating one hydrogen going to azote 13, that will disaggregate in carbon 13 through a beta reaction, and then again you catch hydrogen protons here going to nitrogen 14 and then oxygen 15 and so on. So you can turn here around. At some point you release here an alpha particle. So the net product of this cycle is to take 4 hydrogen, one here, one here, one here, and the last here, and you release one helium. So basically you just convert hydrogen into helium. You have here a bottleneck at the nitrogen 14. The reaction of disintegrating of catching these protons on the nitrogen 14 is the slowest of all this reaction. So the net effect of this cycle is to convert all your oxygen and carbon inside your convective core here into nitrogen 14 in these stars. What is important as well is that you change this different number of carbon, oxygen, converting them into nitrogen, but the number of these atoms is constant over time because they are not used anymore. You just catch protons and release an alpha particle at the end, but the number of these catalysts is constant over time. So this is for the hydrogen burning. So for low mass stars, you use the PP chain that directly burns the protons into helium, a bit it was done during the primordial nucleosynthesis. For more massive stars, this chain here becomes the dominant one in the production of helium. But the net effect of both chains is to convert in the core of your star the hydrogen into helium. So then when this is done, the star has to contract because the energy production in the core is not sufficient to counteract the gravitation. So the core of the stars will collapse, will heat, and will get to higher density up to a point where it is able to start a new burning phase. The next burning phase is a bit, it took time to people to understand how stars can go through helium burning, because the only way to go to higher mass elements is to use the triple alpha reaction, and as we have discussed during the primordial nucleosynthesis, it's very hard to go through this kind of elements because their lifetime is extremely short. So to go through, you need to have a density that is high enough and a temperature that is high enough to allow this second reaction here, a capture of an alpha particle by the beryllium-8 that is faster than the disintegration rate of beryllium-8. That is very fast. So this is a kind of miracle that occurs in nature because the carbon-12 has an excited level that is very close to the sum of the mass of these two elements here. And that increases quite a lot the probability of reaction of this reaction. And it is Hoyle in 1954 that predicts this level excitation at 7.7 MeV for the carbon that to explain the observed carbon-12 abundance in the universe. So this resonance here ease a bit this reaction here and allows the triple alpha reaction to take place in stars. So basically, you take 2 helium-4 nuclei to make a beryllium-8 atoms, and then you have to be quick enough, so quite high density, quite high temperature, in order to allow these atoms to capture another helium-4 before it disintegrates, going through the production of a carbon-12 core. The carbon-12 is a very stable atom, so once you have produced this kind of nuclei, the job is done for this reaction. This one is stable. You can see that again this reaction is extremely energetic. Its dependence on the temperature is very high, temperature at the power of 25. So again, it will be extremely peaked toward the center of your stars, and this explains why in stars this helium burning occurs in a convective core again. And the energy released by the reaction is lower than what is produced during the hydrogen burning as well, meaning that you need more reaction to sustain the luminosity of the star, and this explains also why the duration of this phase is shorter than hydrogen burning. You need to burn more quickly your fuel in order to sustain the luminosity of the star. So once you have your carbon inside your core, you can, during helium burning, you can go a bit further using this reaction here. So I did not explain this kind of notation previously. I don't know if you're used with them. You have usually the initial atoms here, and then in the first part of the bracket you have the particle that is captured, and in the second part the particle that is released during the reaction, and then the final product here. So basically here it means that carbon-12 nuclei catch an alpha particle, so a helium-4 nuclei, released 1 photons and becomes oxygen 16. Once you have oxygen 16, you can still go to heavier elements by again capturing an alpha particle and producing neon 20. This depends really on temperature. So the higher temperature you got in your core, the more towards neon 20 you tend to go. So basically, this kind of reaction can occur in the more massive star preferentially. 2 other reactions that are interesting, we'll see later why. It's because they are neutron source, in that you can have carbon-13 in your core that will capture an alpha particle and release a neutron to produce oxygen 16. And as well here, you have this chain of reaction between nitrogen 14, fluorine 18, oxygen 18, neon 22. And neon 22 can react in 2 different ways with the alpha particles that are in the core, or going through this channel with an alpha captor and a photon release making magnesium 26, or going through these alpha captors and neutron emission producing magnesium 25. But these 2 reactions here are important because they can be a source of neutrons, and we'll see later why it is important to have neutrons in different phases of the stellar life. So this helium burning is basically the end of the evolution for stars that are less massive than about 8 solar mass, because at the end of this reaction, the stars will start to contract and heat again, but they will enter the degenerate gas region, and progressively the electron degeneracy pressure will be able to counteract the gravitation. So you don't need to contract more in this case, and these stars will end as a degenerate core of carbon and oxygen, and will produce this carbon-oxygen white dwarf that are just core of about 1 solar mass stars sustained by the electron pressure degeneracy, the electron degeneracy pressure. Sorry. From this point, you have also a decoupling between what happens in the core of your star and what happens in the envelope. So basically, in the envelope, the reaction time of your envelope is the Kelvin-Helmholtz time, so the thermal readjustment time of your envelope, which is given by this relation here, which is typically 10 to the 5 or 10 to the 6 year for a typical star. On the contrary, what happened in the core is that the typical evolution time scale for the core is the time scale of the contraction and the time scale of producing carbon of the carbon-12 burning. So it becomes typically this kind of thing. So this is the potential gravitational potential energy, and here it's the energy of the core divided by the luminosity. So you get something about 1,000 years for the core. So it means that the typical evolution time of the core is several orders of magnitude faster than the envelope. So what does it mean here? It means that your envelope will not react fast enough to whatever happened in the core. So basically from this point, the surface of your star is no more affected by what happens in the central region. So for an observational point of view, your star will no more evolve. In the Hertzsprung-Russell diagram, for example, the temperature will remain constant. The surface temperature, the surface luminosity, and so on will remain constant from this point. So for the more massive stars that are not sustained by the degeneracy pressure, the core will continue its contraction and heating and going to denser state up to the point where we can ignite carbon burning. So typical temperature for carbon burning are between 500, 800 million Kelvin. And the main reaction from here is the capture, the fusion of two carbon-12 atoms that will go to an excited state of magnesium-24, and then this magnesium-24, depending on the conditions a bit, can go through different channels producing neon-20, sodium, natrium-23, magnesium-23, and so on. Most of the channels go through these two here, about half-half. This reaction here is quite rare because it is endothermic, so its probability to occur is much less than the two other ones that are exothermic. You can also go through, once you have produced this kind of nuclei inside your star, you can go through different other secondary reaction with a proton capture on top of the natrium-23 producing neon-20. The neon-20 then can produce magnesium-24 and aluminium-27, or the oxygen-16 can also go to produce neon-20. The main products of carbon burning are neon-20 and magnesium-24, and the proportion is roughly 3 neon-20 for 1 atoms of magnesium-24. An important thing here is that from this reaction you produce a lot of neutrino. This was not the case during the first cycle of hydrogen burning, of helium burning, but the reaction concerning the carbon burning and the successive reaction that will take place in the future from carbon burning produce a huge number of neutrinos. And the neutrinos are particles that interact very, very few with the ordinary matter. So basically, this neutrino will escape the star without interacting with nothing inside the star. So they will take a lot of energy away that is not used to sustain the star, because you have no interaction with the matter. So this will not heat the matter and produce the pressure needed to sustain the gravity. So this is another reason why the burning phases from carbon burning becomes so fast. It's because you have only a very small fraction of the total energy produced that can be used to heat the medium. So you need to go very quickly through this cycle to be energetic in order to sustain the star. So the fuel is burned very, very quickly. So when you have produced your neon 20, the next phase of the main burning phase that occurs after carbon burning is a neon photodisintegration that occurs at temperature around 1 billion Kelvin. So the main reaction here is the photodisintegration of neon 20 that absorbs a photon and releases an alpha particle to produce oxygen 16 again. As you have this reaction that produces alpha particles, these alpha particles can be used by other neon atoms to produce magnesium 24. And once you have magnesium 24, you can use this alpha particle released here to produce silicon 28 as well. So the main products of neon photodisintegration are oxygen 16 and magnesium 24, and the proportion is roughly 1:1. Then, again, your star will contract, reaching higher temperature, and when it reaches central temperature of about 2 billion Kelvin, oxygen burning can begin. So basically, you will fusion 2 oxygen 16 atoms, producing sulfur 32, and then sulfur 32 can disintegrate in different kind of channels, producing phosphorus 31, silicon 28, sulfur 31, or phosphor 30, producing different kind of energy. But the main products of this phase is the production of silicon 28 and sulfur 32. Then, again, you will reach higher temperature, a few billion Kelvin, and from there you will have a quick photodisintegration of the silicon. So the silicon will melt in some sense. It will start to strongly interact with the photons that will progressively destroy it, starting from silicon 28, releasing an alpha particle going to magnesium 24, neon 20, oxygen 16, carbon 12, and at the end you will produce only alpha particle through this channel. But all these alpha particles that are released from a fraction of the silicon 28 will be used to produce some subgroups in quasi-equilibrium, starting from the silicon 28, for example. Other atoms of silicon can catch one of the alpha particles released here to produce sulfur 32, and so on. You will produce these different kind of elements in quasi-equilibrium, and progressively you will go toward the more binded nuclei in a nuclear statistical equilibrium. So the main products of this different phase of burning are the multiple of alpha particles. So you will have everything that is a multiple of 4 here, and towards the iron peak. So basically up to the nickel 56. What happened then is that it's the end of the possible hydrostatic evolution of stars, because you reach, here is the curve that tells the binding energy of your nucleon as a function of the mass number, and you see that the more binded atoms are the iron one. So as soon as you start here going towards iron, you are able to extract energy from fusion process. But once you reach iron, if you want to fusion iron with something, it will not produce energy anymore, it will consume some energy. So basically, when you have reached the iron or nickel 56, you have no way of burning things in your star and producing energy on the same time. So you will produce no species heavier than the ones of the iron peak through this process. Then, depending of your mass, you will end in different kind of thing. the low mass stars will end as a white dwarf, as I mentioned. And these stars are mostly sustained by the electron degeneracy pressure. And some of these white dwarf will be in binary systems. So basically 2 stars that are rotating around each other. So here is a small sketch of what happens to this kind of system. You have 2 stars of different mass on the main sequence. At some point, the more massive stars will become a giant, and the other one continue its evolution. Then this star here ends its evolution, produced a white dwarf, and the other star that is slightly less massive will at its turn become a red giant, and the secondary stars here can become to accrete material from this star. Due to its radius inflation, these stars become huge, so it becomes easy to transfer mass from this star to the white dwarf. And progressively, the white dwarf will accrete matter, and it can reach at some point what is called the Chandrasekhar mass. So the Chandrasekhar mass has this expression here and is about 1.4 solar mass. And it is the maximal mass that can be sustained by electron degeneracy pressure. If you go above this mass, you will suddenly produce carbon burning deflagration at the surface of your star, and this will explode your star, producing what we called type 1a supernova. So this will completely disrupt your white dwarf, producing a lot of nuclear burning during the explosion, and this will produce elements up to the iron 56 as well. So basically the reaction produces nickel 56 that disintegrate into cobalt 56 and then iron 56, which is the most stable nuclei in the universe. So these supernovae have very peculiar light curve. You have a strong peak of luminosity during the explosion of the supernova, and then you have 2 successive slopes in the light curve. The first one corresponds to the half-life of the disintegration of the nickel 56, and the second one corresponds to the disintegration of the cobalt 56 into iron. So these 2 disintegration heat the matter during the explosion and allow the supernova to be bright, with the luminosity decreasing according to their disintegration law. One great thing with this kind of explosion is that as they occur roughly all at the same mass, because it happens close to the Chandrasekhar limit, they have all the same luminosity at the peak. So we can use these supernovae as we call standard candles. It is some object that we know their luminosity, so we can use them to measure the distance in the universe. And as these supernovae are extremely bright, we can observe them from extremely far away. So they are a powerful tool for measuring the cosmologic distance in the universe. And it is with this kind of observation that we discovered quite recently that the expansion of the universe was accelerating again by comparing the distance of supernovae, type 1a supernovae, comparing to what we expect according to different kind of models for the evolution of the universe. So this was one of the Nobel Prize, I don't remember the year, a few years ago. So this is what can happen for the low mass stars that are in binary systems, and thus it's a way to produce the iron peak elements in the universe. Indeed, most of the iron and iron peak elements come from this type 1a supernova because they are completely disrupted. So at the end, all the matter of the star is released in the interstellar medium. The more massive stars have another kind of end. They go through type 2 supernovae. So at the end of silicon burning for these stars, you have no more energy to counteract the gravitation, and thus the core of your star will collapses very quickly. So this is illustrated here in this plot. So you have time here in milliseconds, and here is the end of the nuclear burning, and here it's the radius of your star, and the lines here show isomass location. So basically, when these black lines go towards the center, the mass is collapsing towards the core, and when the lines are going outwards, it means that they are ejected at bigger radius. So what happens is that at the end, the core contracts very quickly and produce a neutrinosphere. So the gravitation is so strong that the only way for the protons produced that are present in the matter of the core to counteract, because protons tends to push them away together due to their electrical charge, but gravitation is so strong that they will force the protons to convert it into neutrons to stabilize the matter. So you will produce a sphere of neutrons, a core of neutrons in your inside your stars, and this produced a huge amount of neutrinos that are emitted in a very short time. So to convert the protons into a neutrons, you have to emit a neutrino. So these neutrinos will form what is called a neutrinosphere around the proto-neutron star, and the external layer of the star will react with some delay. So you can see that the core contracts very soon, but the outer layer starts to fall towards the center later on. And they will find this neutrino trying to escape, and these neutrinos are thought to be able to push away the matter of the external layer and produce the explosion of the supernova. In the shock that is propagating outwards, you have a very high temperature, and so you will be able to produce some new kind of nuclear reaction in a way we call the explosive burning. So the shock will cross the outer layer of the star that have different kind of chemical composition depending on where they were located inside your stars and what kind of nuclear burning they had during the past evolution of the star. But this shock will re-inject energy in this layer and will produce a new burning episode in this layer. So this is a point where we need to focus a bit more on the neutron that exist inside the star in different places. So the neutrons you have neutron captures inside your star, and you can have them in two different kind of flavors. There is a rapid neutron captors or the slow neutron captors. So this is why you have the S process and R process for slow and rapid. You have slow neutron captures when the time of beta disintegration of your atoms is smaller than the typical time for capturing neutrons. So in this case, the beta reaction will win against the neutron capture, and you will basically follow a given path in the nucleosynthetic diagram. So this kind of process occurs in red giants, in AGB stars, and in massive stars in different kind of layers where you have these neutron sources. So we show this different reaction previously here. So these two reactions are able to release neutrons that can be used by other kind of nuclei to produce other elements by neutron capture, and then a beta disintegration, and then maybe a new neutron captors and a beta disintegration, and so on. Typically, the neutron capture time is about 10 years in this kind of process. You also have the rapid neutron captures, where here the time of capturing a neutron is much shorter than the beta disintegration time. So this happens when you have a lot of neutrons in your medium, because you need to capture a lot of neutrons to go through this process. So this is typically the case here when you produce this neutrinosphere, when the neutrino will go through here and produce this shock where you will produce new nuclear reaction in the envelope. You will produce a lot of neutrons here, and this is a typical place where our process can take place. So in the supernovae, at the interface between the neutron star and the iron shell, you will have a lot of neutrons that will allow you to capture a lot of them on different nuclei. The neutron source are the conversion between protons and neutrons, obviously, and the typical time for neutron capture is 10 to the minus 6 seconds. So here is a small plot showing how things evolve. So you have here, again, you have here the Z, so the elements is here, the atomic number is here, proton number, atomic number, and you have here the stability value here in the middle with in black some elements that are stable. And then the movie will show you how, when you inject a lot of neutrons in this medium, how elements will be changed in new ones through the R process. You capture a lot. A lot of neutron captures will push your elements to the right at different places, and then due to beta reaction, progressively they will go up toward the stability value. And from this initial composition here, you will shift your new composition at higher isotope number, proton number, and atomic number. So this is a way to producing elements heavier than the silicon, the nickel 56, or below the iron peak. So I will start it again. So first, you inject a lot of neutrons, neutrons capture that push everything to the right at the same Z number, but increasing the atomic number, and then the beta disintegration that progressively brings everything toward the stability value. And the colors codes the element that are the mostly done, so they are close to this line here that are the super stable elements. So with this kind of process, so the S process and the R process, we are able to explain some of the patterns that are shown in the solar abundance. So the observational points here are what is observed in the sun for different kind of elements, and the green and red line show the contribution that comes from the R process and the S process. So you see that you have elements that are typically produced by S process, for example this one here, and other one that typically comes from the R process, depending on what kind of nuclear you are looking at. So you have elements in the sun that you know that they should come from S process or R process because they have different abundances relative to hydrogen that cannot be explained by other means. So if we go back to this plot here that I showed you at the very beginning of my talk, so you have here the solar system composition with hydrogen, deuterium, helium, and so on. So we know that these different kind of elements come from different nucleosynthesis. So up to helium, it comes from, obviously, from helium burning. You can produce carbon, oxygen, neon with helium burning. Then up to here, carbon burning, up to silicon roughly. Oxygen burning can go up to sulfur, for example. Silicon burning is able to build all the elements up to the iron peak and the nickel. And then all the other elements that are heavier than the iron peak here comes from neutron captures at different places inside stars at different stage of their life, or in the slow version or in the rapid version. but it is the only way to produce this kind of elements here. So we started from hydrogen, and we are now able to have the elements for doing scale, feather, hair, bacteria, what you want. So starting from the Big Bang and almost nothing except hydrogen and helium, the matter through the stellar cycle, through their processing in one or several generations of stars, are able to produce all the elements that are needed for developing life, at least on Earth. So how can we translate this nucleosynthesis inside stars in terms of chemical evolution of the universe? So the enrichment is progressive and depends on where your supernovae explodes and release the matter from the stars inside the interstellar medium. So you have here what happens at the very beginning. So you have a homogeneous medium a few times after the Big Bang, and then you have the first star that starts to explode and progressively enrich the medium around them. As time proceeds, you have more and more supernovae explosion that progressively fill your space, and with some place where you have effects of several supernovae, and so on and so on. So progressively you enrich the universe by exploding supernovae that enrich the medium around them, and at some point you finished with a universe that is quite enriched everywhere. The stellar formation is progressive or induced. It depends. So you can have stars that forms continuously in some medium, or sometimes you have induced stellar formation when you have, for example, a supernovae exploding close to a molecular cloud that can destabilize it and making it collapse. So you will produce induced stellar formation at this point. So the gas is progressively incorporated in stars. This is shown here. So for example, here you have the time starting from 0 up to now, and you have the different the total mass content of your galaxy. And here is the fraction that is incorporated in stars, and here is the fraction that is incorporated in gas. So from the beginning, for example, basically your galaxy increases its mass with time. At the beginning, all of the mass is composed of gas, but then after some time, stellar formation takes place, and at the end, you finished with a galaxy that is dominated by the mass of the stars and with almost no more gas. Here you have the effect of the enrichment. So again, the time here, and here is this famous metallicity. So everything that is not hydrogen and helium is counted here. One is the metallicity of the sun. So about 1.5% of the mass of the sun is composed of what we call metals. And here is different location inside the galaxy. So this is for the inner region of the galaxy. These are somewhere in between in the galaxy, and here is, for example, the outside location inside the galaxy. And you see that the enrichment occurs at different speed depending on where you are in the galaxy. So in the central region, for example, you enrich extremely quickly your medium, as in the outer layer, the enrichment is more slow and continuous. You have a very different lifetime for stars. As I mentioned, the lifetime of a star is proportional to its mass at the power of the -2. So the effect is that the massive stars can explode quite quickly during the history of the universe. So and the effect of massive star is mostly to enrich the universe with alpha elements, the multiple of 4, typically carbon, oxygen, neon, and so on. So this enrichment in alpha elements will start much sooner than the iron that comes, for example, mainly from the explosion of the type 1a supernova that results of the explosion of these low mass stars that are in binary systems. But the lifetime of binary stars is so long compared to the one of massive stars that the enrichment in iron is much slower than the enrichment in alpha particles, for example. So we can try to check this by finding the older stars of galaxies, because the older stars are supposed to be the less enriched. So we can try to find this kind of stars to check the evolution of the chemical composition of our own galaxy, for example. So the older stars are mostly found in what we call the galactic halo. So I don't know if you're familiar with what is a galaxy. So this is typically a galaxy as the Milky Way, for example. It consists of gas and stars. For example, you have something like 200 billion stars in the Milky Way that are in different locations. You have a galactic bulge, which is composed of quite old stars, red stars. Then you have the disk surrounding the bulge, where you can have spiral arms, and the gas, you have gas and dust inside these arms, where you have star formation. So you have more blue stars, young stars in the arms. The sun is somewhere here, so in a bit after the middle of the radius of the disk of the Milky Way. In terms of size, the size of the galactic bulge is about 4 kiloparsecs. The size of the galaxy in diameter is about 30 kiloparsec, and the sun is roughly located at 8 kiloparsec from the center. And you have, surrounding the galaxy, you have what we call the galactic halo, composed of very old stars and low mass stars, and globular clusters as well that are structured with several thousand of stars in them. So to find these old stars, we have to look preferentially in the galactic halo, and we found a couple of them. So the historical reason is that if you look at the sky by summertime or at the mountain during winter, you will see the Milky Way as a kind of whitey, milky trace through the sky. And the Greek at the time of where they put name on things called them Milky Way because of that, and because there should be a history with, I don't remember if it's Hera or I don't know who from the Greek mythology that spread milk somewhere during his life, and yeah, in remember of this story they called it Milky Way. But it's due to the fact that it appears really as a white trace through the sky that is surrounding us. You have to imagine what you would see from here, looking around you here. So you have this disk that is quite thin. So it's a band that is just everywhere around us. Okay, so we had look for these stars, and a few people have found during the last 10 or 15 years a lot of them now. For example, you have this kind of red stars here in the halo, which has this fun name here, with a metallicity of -5.3. So it means that this bracket notation here means that the iron content of these stars compared to the sun is 10 to the -5. So there is 0.00001 times the iron contents of the sun inside this star. So it's very low metallicity. There is another one here, which has still a lower iron content, 1 over 1 millionth time the contents of the sun in terms of metals. These two are evolved stars. We have also here probably a main sequence star that has also a quite low metallicity. It's less, but this is a main sequence star. The other one are evolved stars that are a bit easier to find than the main sequence one. I did not update these slides. Maybe there are a few more now at around, yeah, the typical metallicity of 1/10⁶ times the solar iron composition. So there is, all the stars have not the same metallicity inside the Milky Way. So you can put some stars and see how they are distributed in terms of metallicity, and you will find this kind of distribution here, or this kind of thing here. The observed points are the stars here. And you can check if we are able to produce models of the evolution of the chemical composition of the Milky Way, and check if they are able to reproduce the observed metallicity distribution of stars in terms as a function of time or as a function of the metallicity here. So it appears that the models, the chemical evolution models, are quite, yeah, it's not perfect, but at least we are able to more or less reproduce the metallicity distribution of the stars, even the very low metallicity stars here. Yeah, here the shape is not exactly perfect, but at least it's a step toward the good direction. Again, we can try to constrain to check or constrain the stellar models by trying to reproduce what we see around us. So you have here the nitrogen to oxygen ratio or the carbon to oxygen ratio as a function of the oxygen to hydrogen ratio for different observed stars here and here. And if you take stellar models with slow rotation up to this metallicity here, you find that we should have this kind of trend here that are not very good for the N/O ratio here particularly. And you can try to see what happens if you consider that you have at very low metallicity, instead of non-rotating or slow rotating stars, you have very fast rotating stars at some point. And you see, for example, that adding rotation, fast rotation in stellar models allow to better reproduce this point here or this point here. And to check the observation, these are observed stars. We can also observe DLA systems that are measurement of the chemical composition of the gas, interstellar gas, instead of directly measuring it in stars. And you see that the agreement is as well quite good with respect to what the models predict. So this kind of chemical evolution model for galaxy can be used as test for stellar physics as well. And we are able to see that we need at least maybe a bit of rotation, fast rotation at very low metallicity to explain the trends we are observing. So there is also an interesting point in that to produce planet, it seems that we need a minimal metallicity as well. So here again, the metallicity distribution of stars that host a planet. So you can see that most of them are around solar or above, and very few goes to lower metallicity. So again, it means that to build up planets around a star, maybe we need a minimal metallicity for the star. It's maybe not extremely surprising in the sense that you need something to build your planet. At least if you want a rocky planet, it may be less true for the giant planets. But nevertheless, it seems that you cannot probably make planet very early in the history of the universe. You have to wait that your universe is rich enough in metals to build planets. And here again, it's the same distribution of metallicity for different planets, so with different kind of radius. Planets that are smaller than 4 Earth radii and bigger than 4 Earth radii. And again, even if the distribution seems to be slightly different, it seems that you cannot produce very small planet below metallicity of roughly -0.5 or something like that. So it seems that contrarily to what we learn in some books, the whole story takes a bit more than 7 days. But at least we're here, and yeah, starting from almost nothing, hydrogen and helium. I hope I succeeded in explaining a bit to you how you go to all the elements we can find here. And yes, don't forget that removing the hydrogen you have in your own body, everything else has at some moment have been inside a star at some point. Yeah. So I think I will stop here. Thank you for your attention. I hope I'm not very... No, it's good. Okay. Thank you.